Hello and welcome back to 15-Minute Math. So we are closing out our videos on limits. We might be down to our last one or two here. Today we're going to talk about an interesting theorem called the squeeze theorem. I'm actually not for sure if that's the official title. That's usually what I've heard it called, the squeeze theorem. I've heard it called the sandwich theorem. But I like to call it the squeeze theorem. There's actually another theorem called the ham sandwich theorem. That deals with something totally different than limits. So I like to call this the squeeze theorem, not to get it confused with that other interestingly named theorem. If you're interested, I believe Numberphile has a video on the ham sandwich theorem. It might be Hannah Fry, I think, maybe is talking about the ham sandwich theorem, and I've said that enough. I'm starting to get hungry. So let's just go to our topic of the day. So the squeeze theorem. And we're going to get the intuition of this first before we state the theorem. So let's say I had a function. It's just a generic function. I don't know. Looks like a kind of a polynomial here. We'll call him f. I maybe have a second function, g, and again, who knows what the function rule is. It just kind of looks sort of like maybe a polynomial. It might be some sort of bastardization of a trig function and a polynomial. You know, you kind of see that like sine of x plus x or plus x squared kind of looks like that sometimes. Anyway, so there's f, there's g, and we have this third function that has the interesting property, and we'll call this green function h, but h is always less than f, the black function, and it's always greater than g, the blue function, and those are not strict inequalities, so it could be equal to. And so maybe the graph of h looks something like that. Okay, so we have this sort of hierarchy, right? So maybe I should color code my inequality that I'm about to write. G of x is always less than or equal to h of x, which in turn is always less than or equal to f of x, which is black, so I should write it in its appropriate color. So that's kind of the relationship between these three functions. And what's nice is that I can now say something about the limits of these three functions kind of in conjunction with each other. So here's what I'm going to say. We'll say theorem. If the above inequality is true, and we have a couple criteria here. We have the limit as f of x, the limit of f of x as x goes to, we'll just say c. Let's say that's equal to L. And the limit of g of x, do I want g? Yes, g of x, as x goes to c, if that's also equal to L, then the limit of h of x as x goes to c has got to be equal to L. So that is the squeeze theorem right there. As long as this inequality is true, and we know these two limits are true, this third limit must follow. Just because of this inequality, right? If h has to always be bigger than g, or at least equal to g, and smaller than f, or at least equal to f, and these two limits are L, then h has also got to be L. There's no other option, and you can see it in the picture here. Right here is our point C. And you can see f, the limit as we go towards c of f is this value. The limit as we go, now let's talk about g. The limit as we go to c for g is that value. And since h has to be in between those two things, they kind of squeeze that limit into being. Like h has got to be that same limit because of this relationship, right? I mean, h is always between f and g. So if f and g both go to the same point, h has no other option than to go to that point because h is always squeezed between those two functions. So that's why we call it the squeeze theorem, because you know, you kind of have that squeezing action where you're forcing h into a limit. And I know that doesn't seem useful, and honestly, you don't use this a heck of a lot, but there are some cases where that's about the only hope that you have for finding a limit. So let's do an example where we have to use the squeeze theorem, or at least as far as I know, you have to use the squeeze theorem. There may be another way to do it, but I've never seen it. So let's try to look at, let's consider this function, f of x equals, actually, since we've kind of got this all written out, let's just go ahead and call this h of x, I suppose. H of x equals 1 over x squared times the sine. I messed this up. I got things switched around. It's x squared times the sine of 1 over x is actually what I want. And we're going to take the limit. So we're going to find the limit as x goes towards 0 of h of x. So that's what we want to do. Notice that we can't just plug this in, right? Because then we'd have division by 0. That's a big no-no. We can't use any of our techniques that we discussed in earlier videos. You can't factor the sine function. You can't really rationalize anything. There's no radicals involved. There's a fraction, but it's not a complex fraction, so doing that whole multiply by the LCM is probably not the way to go. We're kind of stuck here. I mean, there's not a lot of good ways, you know, from our previous methods to do this. So this is why the squeeze theorem is the way to go here. And so here's what we should probably do. We're going to find this limit, but first, just bear with me. First of all, we know that the sine of 1 over x is always between -1 and 1, right? I mean, that's just kind of the property of the sine function. The argument here doesn't matter, right? The sine of anything is always between -1 and 1, right? It's at its minimum when you're taking the sine of, what, -90 degrees, and it's at a maximum when you're taking the sine of positive 90 degrees. But you know, that function oscillates between those two values. Now, that's not exactly what we want. We want to look at x squared times that. So let's just multiply through by x squared. So we have negative x squared is less than or equal to x squared sine 1 over x less than or equal to x squared. So all I did was multiply through by x squared because I knew that even though I knew this fact about the sine of 1 over x, I don't really care about the sine of 1 over x. I care about x squared times the sine of 1 over x. So I just multiply through by x squared to get it exactly the way I want it to look. But look what I've done now. I've created this inequality that the squeeze theorem relies on. So in this case, g of x is this function here. H of x is this function here. And f of x is this function here. So let's see, remember what the squeeze theorem also relies on. It relies on the fact that we can find the limits of these like lower and upper functions here. So let's see if we can find the limit of g of x here. We're going to take the limit as x goes towards 0 of g of x. But remember, g of x is just negative x squared. And that's a polynomial which is continuous everywhere, and our strategy for finding the limits of continuous functions is just to plug in the value. So if I just plug in 0, I'm going to get that limit to be 0. And f of x here, we're going to take the limit of f of x as x trends towards 0. And again, I mean, this is a continuous function, right? X squared is a nice polynomial, continuous everywhere. We could plug this in. We get 0 here. So that's good because the squeeze theorem kind of hinges on the fact that these limits are the same thing. Notice that these are both L, right? If this was like L and this was some other number, L plus 5, we can't make that same assumption. They have to be the same thing, which luckily is exactly what we got. So by the squeeze theorem, the limit as x goes to 0 of x squared sine 1 over x is equal to 0. Because it's squeezed between these two functions, and they both have a limit of 0, so this one has to have a limit of 0. So kind of a nifty way to find a limit that we would otherwise would not be able to really find the limit of. So there's the picture, by the way. We called this, I think we called this H actually. So I want you to get kind of an intuition of what this looks like graphically. So our g of x was negative x squared. Notice it just kind of tangent to these curves here from the bottom, and then f of x was positive x squared. And then you can kind of see this squeezing happen, right? This h of x function is just oscillating between our green and blue functions. And since these green and blue functions are closing in on 0 as we approach 0 on the x-axis, that oscillation has to get less and less and less, and of course it's forced to be 0 right there at the origin. So now let's go to a famous limit that actually utilizes the squeeze theorem, and that's going to be to find the limit as x goes towards 0 of the sine of x over x. And this requires a little bit of some geometry to come up with this expression that I'm going to show you, but this is a true fact. We don't have enough time to go through it. But there is an inequality that we can arrive just from looking at the unit circle and messing around with some areas. The important relationship, the sine of x over x is always bigger than or at least equal to the cosine of x, and that's always less than or equal to 1. And so if we know that relationship, and again, you can derive that with some unit circle geometry, then we could take the limit of the cosine as we go towards 0. And again, if you think about your unit circle, as we go towards 0, cosine goes to 0. No, I'm sorry, cosine goes to 1. Yeah, cosine goes to 1, sine goes to 0. And if we take the limit of 1 as x goes towards 0, of course that's a constant function that's always 1, so this limit is 1, this limit is 1. By the squeeze theorem, that limit must be 1, which is an interesting result there, because like I was saying, as sine goes to 0, or I'm sorry, as x goes towards 0, sine goes to 0, which is, so you would think maybe this limit goes to 0, but also x is going to 0, so your numerator is getting smaller, but you're dividing by a smaller number, and so it kind of evens itself out. We actually end up with 1. And to give you a graphical perspective, let's go over to Desmos. And so here you can see it. We've got sine of x over x in red, and then cosine in blue, and the constant function 1 in green. And just like we said, cosine's always smaller than the red function, which is the limit we actually want, which is always smaller than the green function, which is constantly 1, or at least equal to, I should say. So again, the squeeze theorem, it lets us it lets us evaluate the limits of functions that we otherwise wouldn't be able to evaluate. It does sometimes require some tricky thinking, so that's why it's kind of one of our last resorts. If we can't do it any other way, sometimes we are like, well, maybe we could think of some clever ways to bound this function in the region that we want to take the limit of, and then if we can do that, then maybe we can apply the squeeze theorem. But this is a limit kind of worth memorizing, honestly. This limit seems to show up quite a bit. So that's why I thought that maybe, even though we didn't have time to work through the geometry of this bounding inequality, we should at least bring up this limit. All right, so I'm thinking, and I want to say this might be our last. No, we have one other limit video, and then we might be moving on. Yep, that is true. One other limit video, and then we're moving on to derivatives. So if you're enjoying this limit journey we've been on, then you can soak it in for one more video. And if you're getting tired of limits, then the end is near, and we're about to switch topics. So just hang with me for another video. All right, I'll catch you next time.